Okay, in this video we're going to discuss a little bit the specific heats in thermodynamics. So before I give a definition, I'm just going to describe a little experiment that was done by Joule. So basically he had a big tank that was full of water, and that tank was well insulated. So it had a good insulation system. Now within this tank there were like two gases contained in these two tubes. So let's say, here we had a gas, and then here basically was the vacuum. Okay, and this is a valve over here, and all this stuff over here is liquid. So he had over here a thermometer. Alright, so the gas, again, make you think about the ideal gas relation. So what he did is that he opened the valve, and all the gas went from this container to this container until everything got into equilibrium. And what he noticed is that actually the temperature of the water did not change at all. So basically was no change in the temperature. So what did he thought about it? So basically, if we use that definition, it doesn't matter which one we use in this case. This definition for the first principle or this one, the conclusion will be the same. But let's work on this one. So in this problem was insulated. So that means that no heat was actually added or removed from the system at all. And then there is no work done by anything on the system. So this was also equal to 0. So at the end, basically, he was just left with the equation that the change in internal energy was equal to 0. Okay, so that kind of make no sense for him initially, because actually something happened. The gas, when going from here to there, I'm sure it produced something happened when the gas was expanded through the pipe. And then, so he had that equation, and on the other hand, he had the ideal gas relation, PV equal to nRT. Okay, so all this is a constant, so it's not needed. So he said, okay, so over here, obviously the pressure did not affect anything, and the volume neither, because we know the pressure can do work. So the term PV, if you think about it, this is kind of work done by the pressure, but there is no work. So at the end, what he concluded is that the change in internal energy over here must be proportional or in function of the temperature only. I know this is not very intuitive, but what's important is the conclusion. Alright? So at the end, what he concluded is that the change in internal energy will be equal to, let's say, a certain amount of mass times a constant C, I call it here CV, times delta T, or this could just be M C sub V dt. The notation is the same. Okay? So what is that term over here? That new term over here, the CV, that would be the specific heat at constant volume for this case. Alright, and if you remember, in thermodynamics you use the capital letters for the full energy, and you use the lowercase letters for the specific energy or specific value. So the same equation we have over there, you could rewrite it as delta U little, so this is capital U lowercase u, will be equal to what? CV dt. Okay, basically lowercase means per unit mass. All right, so from this equation you can see that kind of CV looks like that will be equal to what? Delta U over dt, which is actually equal to du over dt at a constant volume. All right, so that was kind of the conclusion from the Joule's experiment. So what's important over here is that for a gas, the change in internal energy is just in function of the temperature, and the ratio will be given by a constant C sub V that basically will indicate how well that gas is able to store heat. Okay, now the next page I'll give you if you want the more academic definition. Even though this is a mathematical proof we'll do later on in this for this, I'm not going to do it at this time. Okay, so now let me give a definition. So the specific heat is defined as the energy required to raise the temperature of a unit mass of a substance by 1 degree. Okay, so if you want, you can go online. This is not difficult to do at all. There are multiple experiments that will show you how this is done. Okay, but let's say in thermodynamics, the engineer is mostly interested in, so let's say, specific heat at constant volume, the one we just mentioned before, C sub V, but also another one that would be specific heat at constant pressure, C sub P. Okay, and you will see that all the time Cp is bigger than Cv, and you will soon understand why. Okay, So it's very easy to understand. If we have a closed system over here at a control volume, so basically the volume does not change, the amount of energy that needs to be put into the system to raise it by 1 degree is 3.12 kilojoules. So let's say here we have 1 kilogram of substance, and in order to increase it by 1 degree Celsius, you needed to put 3.12. So that means that CV for that substance will be 3.12. Okay? Now, what would be a system that is able to keep it at a constant pressure? So if you think about it, this is not difficult to understand either, but if you have a piston cylinder assembly, so this is free to move up and down. So basically means that if you put more gas, this will move up, but the pressure will stay constant. And if you remove some gas, this will move down, but the pressure will be constant, because the piston head over here is free to move up and down to keep the pressure constant all the time. So it's B over here is B constant, and this system over here will give you constant. So you see that for here, since the piston is moving, it makes sense that the amount of energy needed to raise it, the amount of substance by 1 degree, needs to be more than for the control volume. So here will be the same amount of substance, delta T 1 degree, and CP will be 5.19. Okay? Last but not least, let's talk about the units. Okay, so if we use the definition not for specific values, so this is U equal to M CV dt, this will give you what? CV is equal to the change in energy divided by M dt. So in that case, what will be the units? Kilojoules per kilogram Kelvin. Okay? If we use the definition of the specific, so lowercase u will be equal to CV dt, CV will be equal to delta U over dt, saying that the units will be kilojoules per degree Kelvin. Okay, you'll probably find this one in most textbook, because this one will be per unit mass. So if you needed to have it per mass, you just need to multiply it. Okay, so that will be it for this video. Sorry, one quick correction. Remember that the lower case will be divided by kilogram. So this one will actually also have the kilogram over here. Yeah, the same constant will have the same units, okay? So it will be kilojoules per kilogram Kelvin.